So yes, so I feel like a lot of times for general audience talks in symplectic geometry, they're kind of terrible, at least at the beginning, because you have to say what a symplectic structure is, and I think it's really opaque if you're not familiar with it. So I'm going to kind of skirt this issue and instead talk about Stein manifolds. So a Stein manifold is, so there's a number of definitions, but for simplicity, I'll take it as just, it's a proper holomorphic submanifold X inside of Cn for some capital N. Also, I'm always going to work smoothly, smooth, complex submanifolds. Okay, and now, but my kind of equivalence relation on these things is going to be a bit unusual. So I'm going to be working with these up to, rather than something more natural, like up to biholomorphism, I'm going to work with them up to deformation, which maybe I'll skirt a little bit what this says, but basically I'm going to allow myself to kind of move around among these things, so just kind of look at like pi 0, this space. But what I don't want to allow is I'm kind of always smooth, and kind of more importantly, I don't let anything interesting go to infinity. So, I don't want to do something silly like just like for any one of these things, I just zoom in on a point and now it's just the same as a linearly embedded subspace. So I don't allow that. No, I mean, you can, but really I'm just like looking at like pi 0 of this space, really. Like the connected components of the kind of moduli space, if you like. Okay, so so in particular, and I'll call two things which are the same here as equivalent. So Stein equivalent, so this implies certainly that I'm diffeomorphic, since I'm smooth all the time and I don't let anything go to infinity. This also implies, I'm not going to try and define this, but symplectomorphic, which, yeah. So here, anything like this is symplectic by just omega equals the Fubini-Studi restricted to x. And this is essentially because symplectic structures have a sort of Moser theorem where deformation implies isotopy. And there's sort of a partial converse to this, which is due to Schielebach and Eli Ashberg. Kind of like we have to add kind of an extra hypothesis, but in any case, so this is sort of an aside, I guess, but yeah. So really secretly, I'm kind of thinking symplectomorphically, but anyway, yeah. If you're familiar, certainly think of it that way, but if you're not, I think it's good to think of it as like complex manifolds, but sort of like made squishier so we can kind of like move things around a bit. Okay, so, and now what I'm most sort of interested in is kind of going from diffeomorphic to the Stein equivalent. So kind of main question or kind of question schema is like, what's the relationship between the smooth topology and the Stein types? Okay, so for example, so let's maybe do the easiest possible example. So if I'm going to use lowercase n for my dimension, so if n equals 1, then it turns out that so any open Riemann surface is Stein. In particular, every smooth non-compact surface admits Stein structure. And they're all equivalent as long as they're diffeomorphic. So the only thing we have is
in your original definition, is it proper? Did you mean that this couldn't be the entire space? Or
could be the entire space. Sorry, proper means, I guess in the point set topology sense that, but in other words, like if I take any compact set in Cn, then the intersection with X is compact. So I don't want to have like the disk embedded in C embedded in C2 or anything like that. Going to infinity in X forces me to go infinity in Cn. Okay, great. So now a bit more generally, so another statement is in any dimension, if X is Stein, then X has a homotopy type of a half-dimensional CW complex. So this is just some version of the Lefschetz hyperplane theorem. And I'll return to this later. So now kind of for more, so in particular, never compact, of course. So now let me maybe do some other dimensions. So so for n equal 2, there's kind of a surprising fact, which is due to, this is maybe a little bit of a folk result, but let's say Eliashberg-Gromov, which is that the manifold S2 cross R2 is not Stein. And then, so here we're kind of seeing that, this Lefschetz hyperplane property is not the sort of only necessary property. And I think this is a good contrast with n greater or equal to 3, which this is a theorem due to Eliashberg in 1990, which says that if X has a half-dimensional homotopy type and Tx is complex, just as an abstract vector bundle, then this implies actually that X is Stein. So we sort of see the converse to Lefschetz hyperplane in every dimension, sort of except dimension 2. Yes, yeah. To me, that's equivalent. Yeah. So dx being complex means X is almost complex. Certainly that's necessary, and also in this result, the complex structure induced from the Stein structure is homotopic to this almost complex structure, among almost complex structures. Okay. And now, but even though we have this kind of nice correspondence in high dimensions, there's, so this is sort of an existence result, but we have kind of a failure of uniqueness. So for n greater or equal to 3. So as far as I know, the first example of this is due to Seidel, but not totally sure. But so correct me if I'm wrong, but I'm fairly sure this is the first example, which is that there exists distinct Stein structures up to this equivalence which are diffeomorphic and kind of the same almost complex class. So yeah, we see that in high dimensions, we still have this failure of kind of the smooth topology and the Stein geometry to correspond exactly. Even though we have this existence result, there is not a sort of uniqueness result. Of course, n equals 1 is the kind of only case where we have this perfect correspondence. Okay, so this is sort of just, and this, I forget the date exactly, but I think early 2000s. Okay, so great. So this is just kind of wanting to set up the background. But now I want to talk about how to think about these sort of structures. Okay, so if we're given this x and Cn, then I can think about the function, let me call phi, which just maps to the positive numbers, which is just phi equals just norm square restricted to x. And so this is a pluri-subharmonic function. And there's a number of different ways to say what this means, but the way that I will use is to say the following thing. So I'm going to let y sub c be a level set of this. Let this be a regular value. And then let xi be a hyperplane distribution on this real hypersurface, just be defined by all of those complex tangencies to the manifold. So this xi is just ty intersected with j times ty. Here j is just complex multiplication. So this is everywhere a hyperplane, right? So to say that this is plurisubharmonic is to say that that xi is contact, which means that it is locally equivalent to r to n minus 1, where xi is the kernel of dz minus yj dxj. OK, so what's going on with this? So by being Stein, that means that on every one of these level sets, I get a hyperplane distribution of all my complex tangencies. And I'm claiming that some sort of convexity assumption of Cn is inducing this kind of standard local structure. And what's the kind of interesting property of this is that, so xi is defined by, another way to say it is maximal.
Sorry, I'm a little bit confused by your coordinates. So the xj and the yj are the coordinates of r.
On r to n minus 1. So this
What
is,
the z?
so this is j equals 1 to n minus 1.
And z is the last one.
And z is the last one, yes. Notice that del del z is never in this kernel. So it's kind of like a choice of transversal here is what's kind of distinguishing it. I mean, it's not a canonical direction, but it's that's the reason why we use a different letter. So yeah, it's defined by this maximal non-integrability, which is to say that if, let's say, m in y is any just n-dimensional manifold, then M cannot be tangent to C. And this is even kind of up to first order at a single point. Maybe it makes more sense to say second order. Like second order in M, first order in C, maybe. Yeah, anyway. So yeah. All right. So yeah, the way to think about this is it's very hard to have kind of submanifolds be tangent to this plane field. OK. So now we have, let's say, I want to get back to my kind of Lefschetz hyperplane. So what's the point of this? So I'm going to let, let's say, P in X be a critical point of phi. And I'm going to let, let's say, dkp be the stable manifold. And I'm going to let, let's say, lambda p be how this stable manifold is intersecting y. So then it's kind of fairly easy computation that that this lambda is always tangent to this xi. So what's my sort of cartoon picture here? So I have this manifold X, right, like living inside of Cn. And inside of any level set, I have this kind of hyperplane distribution of complex tangencies that's very hard to be tangent to. And now if we take a critical point and look at its stable manifold, then this, my sort of lambda, is tangent to xi. So immediately, this implies that, so it's hard to be tangent to this if I have too many dimensions. So the dimension of this has to be small. So that implies that the dimension of lambda has to be no more than n minus 1, which then is implying, right, that that this k is less than n, the dimension of the disk. And so this kind of recovers the this Lefschetz hyperplane picture, right, that everything is just a union of these disks. Okay. And now, so what's the kind of important fact is that, so this is kind of main theorem that lets us do kind of anything with these structures, is that these lambda p up to isotopy in y, and this is sort of among tangent manifolds, actually determine x up to this Stein equivalence. So we have, so think of this as kind of very similar to like handle body theory of like, I guess, Smale and then like Milner-Crever, like sort of high dimensional surgery theory. So if I want to understand, like there is just, if you want to understand diffeomorphism types, you just have to understand smooth isotopy types with these attaching handles. Here, to understand the Stein equivalence, you just have to understand the isotopy type. But up to this isotopy among tangent manifolds. And that's sort of where we can begin, I guess. So now there's another kind of important ingredient, which is a theorem due to Gromov, which says that, so here we said that the k is strictly or is less or equal to n. So if this k is strictly less than n, then this lambda is actually determined by just its smooth type, and maybe kind of plus some like normal framing data. So what this is saying is that all interesting geometry is coming strictly in this kind of maximal dimension. So as an example of kind of an application of this, which is more non-trivial than I'm making it sound, but kind of roughly follows from this, is that, so this is a theorem of Schillebach, which says that if x has no critical points of index n, then x is actually equivalent to some x prime times c. But also furthermore, like x prime doesn't contain any data itself. Okay, so this was a lot of classical stuff. So now let me get into kind of some more modern stuff that kind of H principles are doing. Okay, so, and maybe the kind of start of the story is a theorem that it's a little hard to state without going into too many definitions, but so let's just say among n-dimensional submanifolds of contact manifolds, which are tangent to Xi. So these are what are called Legendrian submanifolds. So there exists kind of a prescribed class of these, which are called loose Legendrians, for which smooth isotopy implies Legendrian isotopy. So not everything is loose, and it certainly couldn't be, because if that were true, then diffeomorphism type would determine Stein type for kind of all manifolds. However, if we look at kind of all of the different Legendrian types, kind of realizing a fixed smooth type, it's not sort of just like chaotically strewn about. There's kind of a well-defined sort of minimal Legendrian class in every smooth class, which is kind of, I guess, representing its smooth type, but kind of not having any interesting geometry itself. And I guess what's kind of interesting of this is that you can, there's almost no content to this as stated, but the kind of important part is that you can verify looseness by seeing it on any single open set. So this is still kind of vague, but I think maybe the intuition is more important, which is that if I have some Legendrian and I'm just looking at some small piece of it, and I can see like, okay, on this small piece it's loose, then it doesn't matter what is going on with the rest of it. There's no way to make it non-loose if it's already loose on some small piece. So in some sense, like, to be non-loose, you have to be non-loose everywhere, whereas to be loose, you just have to be loose on a single set. But that's sort of surprising, because then if you're just loose on this single set, then you're completely determined by your diffeomorphism type. So now let me talk about some kind of examples of this, or some applications of this. So kind of following this, this theorem was sort of like brought over to the Stein world to give a similar theorem there, which I'll just write it sort of quickly, but there exists a class of Stein manifolds called the flexible class. where diffeo implies a Stein equivalent. Here I'm being a little vague. So this smooth isotopy is like smooth isotopy with normal framings. Corresponding to this, it has to be diffeomorphic in a way that's like preserving just the complex structure on the tangent bundle. Yeah, there's kind of normal framing data floating around all of this, but it's kind of purely topological. OK, so now maybe
What's the name of this class?
flexible. OK, so now to give some kind of like concrete examples. So let's say we're looking at.
What's an example? You said applications, you also said the word example.
Let's be very concrete now. So I'm going to call xb to be the complex threefold, which is xy to the b plus z squared plus w squared equals 1. So this is in C4. B is a positive integer, yeah. So something that Seidel shows is that xb is not the same thing as x1 if b is at least 2. So, so first of all of these are diffeomorphic. Secondly, so if b is 1, this is just the quadric. And so if b is positive, none of these are equivalent to the quadric. However, sort of surprisingly, is due to Roger Casals and myself, is that xb is equivalent to xb prime if b and b prime are both larger than 2. So yeah. So this seems sort of surprising. Like, why should 2 or bigger be any different than like 1, right? And I think people were sort of surprised by this when they first saw it. So the way to think about this is kind of in this statement that it's possible to verify looseness on a single open set. So when you go to b equals 2, you already kind of get this looseness. And now, which is like some local model, like whatever it is, I don't care. Now when you go to b equals 3, it kind of has more of this. But who cares? Like you either have it or you don't. And once you have it, you're completely determined just by your smooth type. So yeah, that's one example. We were also kind of quite surprised that, so I should say, because these are flexible. I should also say, so these are all diffeomorphic, right? So they're all diffeo to like S3 cross R3. So in particular, I do have some maximal index critical points.
Sorry, is the idea that you check it at 2 and then somehow pass to the higher one? Compare?
I would say you. So you compute it for each one separately, but you don't actually construct the equivalence. You show for each one individually that it's flexible, and then the theorem says they're all the same. Actually finding the equivalence is hard, though. roughly because this theorem's not super constructive. Okay, great. So another example. So let's let x. I should also say here, very important. N is at least 3. There's no theory of flexibility or loose things in 2 dimensions. Yeah. So 3 dimensions is a pretty good dimension. So here's another threefold. So I'm going to let x be x plus x squared y plus z cubed plus w squared equals 0. And this is sort of well known because this is kind of the first example of what's now called Corus-Russell cubics. And it was studied because it's known that x is diffeomorphic to R6, but x is not, let me say, like algebraically isomorphic to C3. And this is kind of shown by kind of studying the space of all like holomorphic or algebraic derivations on this, or alternatively like C star actions. So that has some kind of history for it that I don't know so well, but going back to the 70s. So anyway, so then as another example of this, you can get that x is actually, well, just for emphasis, let me say symplectomorphic to C3. And this is also due to Casals and myself. So yeah, and again, the proof is sort of the same. Like constructing the actual symplectomorphism to C3 is not super explicit. It can be done explicitly. It's not so bad. But really I think the only way you would sort of philosophically discover this is you discover that it's flexible, and then you have this theory of flexibility that says it's therefore C3. I should also remark, kind of as an open question, whether it's like actually biholomorphic. That seems like well, I don't know so much about complex analysis, but that's been open for a long time, and certainly we don't give any tools to approach this, but it's a good question. Okay, great. So I have about 15 minutes left.
These affine surfaces that are they just coming randomly, or how do you make them?
Yeah, it's a good question. And I honestly don't know the answer. So it's more natural from the symplectic perspective. We were sorry?
Not parameter spaces.
No. In fact, we were quite surprised that there were any algebraic examples at all. I think at first we sort of expected them to only kind of be transcendental. Every example we know of looks something like, I would say maybe like a Milnor fiber of like a non-isolated singularity. So here, this is kind of the simplest possible version of this. Here, this isn't really a Milnor fiber, but if you think of this, this happens to be smooth, but is not transversely cut out. So yeah, might have something to do with that, but yeah, I mean, let me write it down then. So how to think about this for affine varieties.
It's just a class. It's like, sounds like the definition of the class.
Yeah, I mean, the definition is kind of purely like you run the Morse theory and then you cut it apart and you do contact geometry. So yeah, I would love it if like there was any interpretation of this like in some like natural, algebraic geometry language, but that's yet to be discovered. Okay. So yeah, so maybe I'll switch gears a little bit, kind of shorter on time than I was hoping to be. So maybe I'll just say as an aside, which is kind of maybe a whole lecture unto itself. Well, actually, you know what, it's just as easy to state it. So let me say it kind of real quickly. So these are all kind of due to, well, let's say Ellie Ashberg, well, Ekholm, Ellie Ashberg, and Smith. And so this is about just Lagrangians in Cn. So one way to say this is, let me just say C3, just for kind of a nice example. So first of all, what's a Lagrangian? So a Lagrangian in C3 is just a three-manifold is Lagrangian if TL is the orthocomplement of J times TL. So think of this as like R3 sitting inside of C3 locally. And it's kind of a big open question in symplectic geometry, like what things can be Lagrangians in here. So what we show is that, so the theorem is that if M is any three-manifold, then M can exsum a single copy of S2 cross S1 embeds as a Lagrangian into C3. This is sort of interesting to contrast the following result. So kind of maybe first you have Gromov's original result, which says that for any Lagrangian, you have that H1 of L with real coefficients is non-zero. And maybe even a stronger version of this is kind of the maximally strong version, which is due to K. Erie, sort of maybe it's good to say like due to Fukaya and Erie, which says that if L is a prime three-manifold, which is Lagrangian, then it follows that L is actually diffeomorphic to S1 across a surface. So yeah, so this is kind of along the same theme of like, you know, there are all these restrictions of like things that you can't do, but as soon as you have like just a little bit to like get outside of this class, right? Like there's just like a little bit to like, you know, not be simply connected or not, you know, a Q homology sphere, not a prime manifold, then you can do kind of absolutely anything you want. It was known for a long time that like with sufficiently many copies of S2 cross S1 you could do this. So really the content is you only need one. Okay.
What is prime?
No separating two sphere. In other words, not to connect some of other manifolds. And there's sort of analogs of this in other dimensions, but let me move on. Okay, so now let me move on just to kind of abstract contact geometry. Where, yeah, this will be fast. So I said that like contact was defined by being locally equivalent to this. So in general, I could say a manifold is locally is contact if it has a hyperplane distribution locally equivalent to this. It sort of overlaps, it's glued by things which preserve this, right? So yeah. So we can ask, you know, what are the contact structures on given manifold Y? So yeah, so now a kind of another theorem that's not directly related to this, but kind of in this same vein, which is due to Strom-Borman and Ellie Ashberg and myself, is that, well, maybe two things. So first of all, if Y is stably almost complex, then there exists a contact structure. So this was sort of known in dimensions 3 and 5 previously, but we proved this in higher dimensions. But maybe more connected with this theme is that there exists a kind of, let's say, smoothly determined class, which are called the over-twisted contact structures, which are kind of completely determined by their just kind of topological data. So that's probably like more or less impossible to parse if you haven't thought about these things. So let me just give a single example to kind of conclude.
That time is only one contact structure on this topological.
not quite. It's saying that for every stable, almost complex structure, yeah, so a contact structure determines a stable, almost complex structure, and in each one of those homotopy classes, there's one. But yeah, so for my example, I was going to say, like, let's let y be S5. And so we can ask, what are the contact structures on this? And so there's something nice about this, which is that y admits a unique, stable, almost complex structure. So all of this business disappears. So so if we define this class by like capital Xi, so this is the the contact structures. So this Xi, this is a monoid under connect sum. So what do we know about this monoid? So we know that it has a unit. So there's a unit which is equal to Xi standard, which is kind of the boundary of C3. So that's a nice thing to know. So if I take Xi standard and connect sum anything else, we get that same thing back. We know that this is not even finitely generated. And so this is due to, maybe Ustalowski and Quan and Van Coort. So Quan and Van Coort say that this is in Ustalowski. I'm not really sure it's in here, but anyway, I would attribute it to Quan and Van Coort, but they attribute it to Ustalowski. So there's a ton of these, right? Like there's like not only infinitely many, but like even infinitely many generators. In fact, they show that there's a submonoid which surjects onto Q, so it's quite large. But so what does overtwistedness tell us? So what this says is that there exists a zero. In other words, we have this Xi overtwisted with the property that if you connect sum anything else, and there's a whole lot of stuff you could connect sum onto it, you just get back this overtwisted thing. So it's this sort of geometry which has this property that it sort of eats or destroys other interesting geometries. And again, this comes from this sort of like local verification property. Like this is overtwisted on some small part, so it is just the overtwisted thing. OK, I'll stop there. Thanks.